All right, so thank you for clicking on this video. In this video, we're going to be looking at some questions that will typically come in paper 1, AQA GCSE chemistry. There are 10 questions. Hopefully, I'll be able to run through them within 35 minutes. Yeah, very, very quickly. Right, so make sure that you got your periodic table. If you need, I don't think that the questions need one, but if you want to have that, it's fine. If you also want to have your calculator, you are allowed to go get that. So we are looking at AQA GCSE chemistry paper 1, questions that will come in the mock, questions that will come in the real paper. So this is it. Most questions here will be combined. The last 2 questions or 3 will also straight to triple. Okay, so these questions are appropriate for those who are doing combined and also those who are doing triple, but the last 3 questions are purely triple questions, and I will let you know as we go through those. Okay. All right, so question 1, before we start, if you're looking for videos like this, you can go to YouTube, Teacher Mr. Wino, and if you go to my playlist, you will not just get videos on chemistry, you also get videos like on maths, biology, physics, and stuff like that. So if you subscribe, then when I upload the videos, they'll just pop up into your phone or into your device, and you can use them to revise. You're also allowed to share these videos with your friend in other schools, and that's really great. Okay, so we're starting now. Question 1 is on atoms, the structure of an atom, periodic table, and stuff like that. And it's only grade 4 questions, as you can see. This will come in triple and also come in can also come in combined science as well. So pause the video and try question 1A and B. Question 1A and B. Pause the video now. Okay, so I will hope you've done that. I'll just show you the answers quickly, and if you got them and you're happy to move on, you can just like the video and move on. But if you want me to run through this very quickly, I'm going to do that. Okay, so I'm going to run through this now. All right, so it says state the relative charge and mass of a neutron. Let me start by answering part B first. An atom has got 11 protons. So that means that in the nucleus of that atom, there are 11 protons. Protons are normally positively charged. So the relative charge of a proton will be positive. It's got 12 neutrons. 12 neutrons are normally found in the nucleus, and they don't have any charge at all. Okay. Now, electrons are not found in the nucleus. Electrons are normally found in the shells as you go around. Okay, they're normally found in the shells as you go around. So the only thing I need here for the nucleus is the 11 protons and the 12 neutrons. If I add them together, 11 plus 12, that's going to give me 23. Okay, and that's the mass number. Now, this seems to be like sodium. The symbol of sodium is Na. So the bottom number is going to be the atomic number, which is the number of protons. That's number 11. And the top number is always the mass number. This is protons and neutrons added together. Okay. In an atom, the number of protons and the number of electrons are normally equal. And that's why an atom is neutral, because the pluses and the minuses, they balance each other in an atom. An ion is different. An ion is an atom that has lost or gained one or more electrons. So this is it. Okay, so I think I've answered the whole of question A, 1A and B. So I've answered that. Okay. Right, so we're going to move on to question 2. Question 2 is on isotopes. They want to define what an isotope is and do some calculation. All right, so I want you to pause question 2 and do question 2. Again, this is just grade 4 to 5-ish, really. Okay, so let's look at, I'm going to look at carbon. We got two elements, two atoms of carbon. We call them isotopes. Now, carbon is atom number 6 because the number of protons will always be 6. However, we got carbon 12 and we got carbon 14. Carbon 14 is very radioactive. It doesn't last long. Okay, but carbon 12 is stable. Now, because the bottom number is the same, the number of protons, the atomic number is the same, but the mass number is different. We call this ones isotopes. So this one will have 6 protons and 6 neutrons, but this will have 6 protons and 8 neutrons. Because the number of neutrons are different, all right, as you can see, this is 8, this is 6, but the proton number is the same, we call them isotopes. Okay, now there's something called abundance. There's something called abundance. Like I told you earlier, the carbon 12 is very stable and carbon 14 is not very stable. So if I pick a sample of carbon randomly in the air or anywhere, you find that most of the carbon in any sample would be carbon 12, but little bit will be carbon 14. The same thing with this chlorine. You have chlorine 35 and you have chlorine 37, the isotopes. Chlorine 35 is most common, that's 75. Chlorine 25, 37 is not common, it's radioactive. So there's no much of it. Okay? So how do we now find an average of these two? That's what we mean by relative atomic mass. And the way you do it, you take the mass of the first one, which is 35, times by the abundance, which is 75%. You can write as 0.75, or you can just write as 75, like that. And then you do the same with the second one. The second one is 37 times by 25. Okay. So you now then add these two together. Once you've added that, then you divide by the sum of 75 plus 25, which is 100. And that will give you the average. This average is called relative atomic mass, AR of chlorine. Okay. So if I show you that, make sure you can define that isotope properly, because they keep asking it in exam. Make sure you can define it properly. Okay, so hope that is fine. Now we're going to move on to question 3. Okay, question 3. Now, question 3 is about sodium and it's about chlorine. I've provided here the structure, the 3D structure of a crystal of sodium chloride, which is the salt used in the kitchen for cooking. Okay, and it's an ionic compound. So pause the video and try question 3. Again, these questions are not hard yet. This is just grade 5. We're moving from grade 4 all the way to grade 9. Okay, so pause the video and try question 3. Okay, right. So I hope that this is it. So now let's look at dot and cross diagram first, because they can ask you about them. So sodium is group 11. All right, this is sodium, is atomic number 11. Chlorine is atomic number 17. All right, that's chlorine. Okay, so sodium on the outside will have 1 electron. 2 plus 8 plus 1 is 11. Chlorine will have 2 and 8 and 7. So you'll have 7 on the outside. Right? So this 1 electron on the outside will be transferred to the outer shell of chlorine. Chlorine nonmetals, they tend to gain electrons. So this is going to be transferred there. And when that is transferred, then this sodium will become positive. Anything that loses electron will have extra positive. So it's positive. And this chlorine now, because it's gained an extra electron, it's going to be minus. The force of attraction between plus and minus is called electrostatic force of attraction, and is always very strong. So this is the molecule. Do you notice that sodium and chlorine, they're in the ratio of 1 to 1, right? So 1 sodium and 1 chlorine. So therefore, the formula for sodium chloride will just be NaCl. So when we write it, we have sodium react with chlorine. That will give us sodium chloride. However, there is something. Chlorine does not occur as an atom. It occurs as a molecule. So this will have been solid. This is gas. And sodium chloride will be solid. Okay? So we need 2 atoms here. So I'm going to balance the equation. So there's 2 chlorine, but there's only 1 here. So I'm going to put 2 here to make this one a 2. This sodium now has doubled, so I need to double this sodium as well. This is the balance equation. Okay. Now explain why sodium chloride has a high melting point. Now look at this structure here. The green is the chloride ion, Cl minus, and the sodium is the black one is the sodium plus, and this Cl minus. These 2 atoms, they've got strong force of attraction called electrostatic force of attraction, which to break needs a lot of energy. So basically this bond here is very strong, and this bond here is very strong, and this bond is very strong. You see that? You need a lot of energy to do that. So because of that, the melting point is very high. All right. There you go. So if you want to look at the answers, now we're going to go to question 4. We're going to go to question 4. Make sure that you can word the answers very, very well. That's why I'm giving the mark scheme. Make sure you can word the answers very, very well. So keywords: electrostatic attraction. The other one is an ionic lattice, which means it's made of positive ion and negative ion to form like a structure, like a 3D structure. Then you have to say a large amount of energy is needed. And then the conclusion, high melting point, because the force of attraction is so strong. To break it, you need a lot of energy. Okay. Now we go to question 4 now. We're going to go to question 4. Question 4 is still grade 5. We start with low grade, then we're going to go up. Okay, a compound has the empirical formula CH2 and relative molecular mass of 28. Determine its molecular formula. Determine its molecular formula. Pause the video and try this. Okay, now I want to run through this, but I want to give an example first. Now let's say I've got glucose in biology. The molecular formula for glucose is always C6H12 and O. This is a molecular formula. The molecular formula tells us in one molecule how many atoms of each are there for each element. So I've got 6 carbons, I've got 12 hydrogen and 6 oxygen. So it tells you exactly. However, we have empirical formula, which is basically the simplification of it, like you simplify ratios, right? So the ratio of 612 to 1 is basically 612 to 6 is 1 to 2 to 1. So for one carbon, we got double the hydrogen and 1 oxygen. You see this? So this one now here is called the empirical formula. It's a simplified version of it. That's what it is. Now, listen. But how many of this would go into that? What do I times this one by to give me that? It's going to be 6, right? It's going to be 6. So I can get that 6 easily. I just need to know what carbon is, the mass, hydrogen, and oxygen. So carbon is always 12, hydrogen is always 1, oxygen atom is always 16. Okay, it's always 16. So what I need to do now, I will need to get the mass of this particular compound, all right, and then get the mass of this and then divide them. That will give me 6. As I can see, for example, you see this is 12. Right? That's just 12. But this is 72. 6 times 12 is going to be 72. So if I do 72 divided by 12, I get that 6. But you do the mass of the whole thing, divide by the mass of the whole thing, and that will give you that multiplier. Do you see that? So I can say that the compound, glucose, one molecule, I can just put 6 here, small 6 down there. It's as if I open the brackets, I'll get that. That's what you need to do with this question 4. Okay, so if you think you can do it now, try it. Okay, now let's look at this now. So the first thing is I need to know the atomic mass of carbon, which is 12. Hydrogen is always 1. So if you double that, that's going to be 14. So this is going to be 14, but that's for the empirical one. The molecular one, which we don't know, is 28. So what do we do with this 14 to give us 28? We need to times it by 2, isn't it? You do 28 divided by 14. That basically means that the molecular formula is going to be the empirical formula, CH2, doubled. We're going to times, put the 2 here. Okay, and then we open the bracket. 2 times 1 carbon is 2, and then 2 times 2 hydrogens is going to be 4. This is it. And if you've done hydrocarbons, this is the formula for ethene. This is the formula for ethene if you've done hydrocarbons. Ethene has got 2 carbons and 4 hydrogens. All right. Okay. Now we go to question 5. We're going to go to question 5, but you want to mark that first. Okay, gonna go to question 5. All right, so we're gonna pause the video and try question 5. Question 5 is now grade 6. So we're starting things up. Pause the video and try question 5. Okay, so with this one, they've said that they want us to work out the volume of hydrogen gas produced. The volume of hydrogen gas that's going to be produced will depend on how many moles is being produced. So the idea is to get the number of moles first of hydrogen. Okay, now we can't do that directly, but we can use this zinc to help us. We can use that zinc to help us because the equation has been balanced. And what that means that for every 1 mole of zinc, you need 2 moles of HCl to get 1 mole of zinc chloride and 1 mole of hydrogen gas. So the ratio of the moles of zinc to hydrogen is 1 to 1. That's the first thing. So if I can work out the exact moles of zinc that was used, and the number of moles, by the way, is always equals to the what? The mass divided by the MR or AR, the atomic mass. Now, the mass of zinc that was used was 6.5. And the AR, the atomic mass of zinc, is 65. If I divide this in my calculator, that's going to be 0.1 mole. So 0.1 mole of zinc was used. That's going to be 0.1 mole of zinc was used. It means HCl was 0.2, you double that. And this is going to be 0.1, and that's going to be 0.1 as well. How do I know that? Because there's one in front here, and there's one in front here. So if the 0.1 is what they use, that means I'm getting 0.1 mole of hydrogen. Okay? And one thing we know that 1 mole of any gas at any room temperature and pressure will always be 24 dm cubed. That's the volume. But you see ours is 0.1. Okay? So what is the volume? The volume is always the number of moles times by 24. That's the formula. Okay? So the moles is 0.1, the volume is 24, and that's going to be 2.4 dm cubed. Okay? And we can times by 1000 to give us in centimeters cubed. We can times by 1000 to give us in centimeters cubed if we want. That's how to do this. Okay? Okay, those are the answers. Now we're going to go to question 6. We're going to go to question 6. Okay. Right, so question 6 is about graphite and diamond. We're still in grade 6. We are heading towards grade 7, 8, and 9. Also, so far, the questions we've done are both for triple and both for combined. Okay, so question 6, I would like to pause the video and I would like you to try them. All right, so I hope that you've tried this. First thing, graphite and diamond are all made of carbon. That's the first thing. They are both of them are made of carbon atoms that are bonded covalently. Okay, remember carbon is at number 6. So that means that on the outside, it will always have 4 electrons. 1, 2, 3, and 4. Because inside will have had 2. The inner shell can only take 2 at the most. So this is just the outer. Now, that means that each carbon is now looking for 4 more electrons to make 8. So one will come and bond there, bringing its electron. Another will come and bond there. Another will come and bond there. And another one will going to come and bond there. So carbon typically has got 4 single bonds around it. Okay. But that is in the case of diamond, definitely in the case of diamond. So for diamond, every single carbon atom is linked up with 4 other. So you see this one has got 1, 2, 3, 4. Each one of them has got 4 bonds around it. Now, which means there's no delocalized electrons. There is no free electrons in diamond. However, in graphite, the business is different. One carbon atom bonds with just 3. Just bonds with 3. So then there's a problem now. See this one? It's a problem. This electron now is got no one to pair up with. So because of this tends to be delocalized. It tends to come up and it can move freely. You see this? And then it can move freely like that. It can then make graphite to conduct electricity. So when you have free electrons that are delocalized, that means that it can conduct electricity, can move around. The electrons can move around carrying charge. That's electricity. So graphite can do that. Okay? Explain why graphite conducts electricity, but diamond doesn't. We will explain that. Graphite has got free delocalized electrons that can move charge, but diamond doesn't. In terms of other properties, diamond is very hard. The bonds are very, very strong. These covalent bonds are very, very strong. Now, graphite is hard, but is slippery, kind of softer, because it is usually, we normally have what we call hexagonal layers. That's a hexagonal layer there, and there's another hexagonal layer here, and in between those layers, there is weak intermolecular force. So there's this layer at the top, another one in the middle, another at the bottom. hexagonal layer forming hexagons. See this hexagon? Can you see that? That's a hexagon and another one. You see? So they occur as layers. So the intermolecular forces between those layers are weak. That means they can slide past each other easily. All right. So graphite is soft in that sense. Okay. So that's just it. They can ask you more still about this, but that's just summary. So look at how the answer has been framed and make sure that you use these words. Okay, so I'll be happy with that. Now you're going to go to question 6. Right, question 6 is about electrolysis. Question 6 is on electrolysis, and this particular question would be triple. However, you can also get other easy questions, which will be on, which will not be on triple, but will be like on combined. All right. So let's just look at an example very quickly. Let's say, for example, and I'll give an example like this. Let's say, for example, I've got a positive terminal and a negative terminal. So you should have done electrolysis. So that's positive, and this is negative. Positive terminal, negative terminal. And then this is an electrolyte. Say, for example, I've got molten sodium chloride. Okay. So molten sodium chloride. It has to be molten. So then the ions are free to move. Now, when you turn the power on, what's going to happen now? This particular ionic compound will break. The sodium ions will break from the chlorine ions. All right. And then what's going to happen now? The positive one will go to the negative terminal. And this what's happened now, ionic equation. Okay. So what's going to happen now is that this sodium ion is going to gain back the electron. It had lost. So you're going to gain back an electron to form sodium atom. All right. And we say that this particular sodium atom has been what? Reduced. Why? Because this an atom doesn't have any charge, but this is a positive charge. Plus going back to 0, it means it's been reduced. Okay. Another way of saying reduce is that when you gain an electron, we say you've been reduced. Now, I can take this electron the other side. Okay, I can take it the other side, and it becomes, this plus becomes minus. So this is the same equation still, same equation. So that's what's happening at the cathode. Cathode is the negative terminal. What about the anode? What about the anode? Positive. The chlorine minus, because it's negative, it's got too much electrons, it's going to lose an electron to become chlorine atom. But chlorines don't exist as atom, they occur as molecule, diatomic. So you need a 2 there, which means you're going to need to double everything here. See? We're going to double that. Now, the charge of this electron has become neutral, has become 0. From negative to 0, it means you're going up. And if you're going up, we say you've been oxidized. Okay? You've been oxidized. Oxidized. But you see that is losing electron. So when an atom or when an ion loses electron, we say that's being oxidized. And this number reduces. That number goes up from negative to 0, it's gone up. So this is what's happening at the anode. This is it. Now, but the other scenarios as well. The other scenarios as well. What about if I had water? And I want you to really listen to this. What about if I had water here? What about if I had water? Then I'll have sodium plus, and I'll have chlorine minus, but I also have hydrogen plus, and I have what? Hydroxide. Now, water, if you pass electricity, will break into hydrogen ions and hydroxide ions. Now, what's going to happen now is this. Because I've got these two positives, the one that is less reactive will go, and the one that's more reactive will stay. Sodium is more reactive than hydrogen. So this hydrogen is going to go to the negative terminal. Okay? It's going to go to the negative terminal. Sodium is going to stay. Okay? Now, when you have a halogen, halogens will always automatically go to the positive terminal. Anytime you have halogen, they'll always go there. Halogens are the elements in group 7, chlorine, fluorine, and so on. So this will stay. So sodium and hydroxide ion will stay to form an alkaline called sodium hydroxide in the solution. But the hydrogen atom will go. So this hydrogen plus, when it goes, is a positive because it had lost electrons. It's going to gain back electron to form hydrogen. But hydrogen is a diatomic, so we need two of them. So we're going to need to double this. Okay. Now hydroxide ions will stay, but chlorine is going to go. This chlorine minus is going to go, is a negative because it's gained electrons, so it's going to lose them to form chlorine. Okay. But chlorine does occur single occurs in twos. So we're going to need to double that and double that. So that is it. So when you have water, then the business changes. As long as you have a metal that is more reactive than hydrogen, hydrogen will displace, it will go. But if you have a less reactive one like copper, that copper will go, hydrogen will stay. Okay? This is it. Now, if we have a sulfate, we tend always to form, sulfate will always just stay. But we tend to form water and retain all oxygen, or both. And we're going to look at this case now. So I'd like you to pause the video and try question 7 quickly. Pause the video and try question 7. All right, so let's have a look. So copper sulfate is CuSO4. Copper has got a charge of +2. It loses 2 electrons. Sulfate ions are always -2. We need to know this. So in this electrolyte here, because it is solution, there is also water as well. There's also water as well. And water will break into H plus and H minus. Now, between these two positives, which one will go to the cathode and which one will stay? Copper is less reactive than hydrogen. So copper will go, hydrogen will stay. So this copper is going to go. And when copper goes, because it had lost electrons, it's going to gain them back. All right, to become copper atom. And since this 2 has gone to a 0, we say it's been reduced. Gaining electrons means you've been reduced. And this number goes down. So this is happening at the cathode, the negative terminal. Okay? Now, at the positive terminal, what is happening? Water is going to be formed. The hydroxide ion, this OH minus, okay, is going to, OH minus has got electrons, it's going to lose them. You lose electron. When you lose this electron, it's going to form something. It's going to form oxygen, and it's also going to form water as well. So these two are going to be formed. That's the first thing. Now, let's do the balancing. There are 2 oxygens here, and there's only 1 here. If I double that, that will give me 2 oxygens, and that means I need 4 there. And the hydrogens are also going to be 4. So that means I'm going to put 4 here. Do you see this? So this is what is happening at the positive terminal. Water is being discharged, and oxygen and what's being discharged. So what you're going to see coming, you're going to see bubbles of oxygen coming, as you can see this one. All right. Now this equation we've written here, we can bring the oxygen this side, and we can leave the water the other side. And I think in the mark scheme, that's what they've just done. But the idea is the same thing. So I'd like you to mark that. Okay, now we're going to go to question 8. Wow, question 8. Hopefully I'm going to be able to do this quickly. Now question 8, it says, a simple chemical cell can be made by placing 2 different metal electrolytes into an electrolyte. Right? Now, this is triple. If you do combined, you don't need to carry on anymore. Question 8, 9, and 10 are purely triple. So if you're doing combined, you don't need to know this. But those who are doing triple need to pay attention. All right. So I want you to pause the video and try this. Maybe if you are doing your year 11 mocks, maybe you haven't done chemical cells yet. But if you cover it, then this question can come in your mock. But definitely it can come in your final Gcse. So it's important that you know how to do it. And this is grade 8. Right? So pause the video and try question 8. Okay, now listen very well. If I have what you call an electrolyte is anything that if it's in a liquid form, it can conduct electricity. And it can be anything. For example, I can have sodium chloride solution. Also, sodium chloride molten. So if I dissolve sodium chloride or I melt it, it can become an electrolyte. It can conduct electricity. That's the first thing. Now, if I've got 2 metals, got one metal on one side and one to the other side. And as long as they have different reactivities, potential difference is going to be generated. Current is going to flow. Okay, and that's what we're going to be looking at in a minute, how this happens. And that's how the cells work. The batteries you buy, that's how they work. You got two terminals. One is positive, one is negative. And then you have an electron right there. And there's some chemical reaction going to happen. And I will explain to you in a minute how this one happens. Right? So let's say I've got magnesium. I've got magnesium there. All right? And I've also got another one. Let's say I've got copper. What's going to happen now when you turn on what's going to happen now? Chemical reactions are going to start happening. As long as they are different reactivities, and there's an electron here, what's going to happen now? They will start losing electrons. Magnesium loses electrons, 2 electrons. Copper also loses 2. The one that is more reactive is the one that's going to release more faster. So this one is made of magnesium. It means that this metal is going to undergo this, it's going to release electrons. And these electrons, what's going to happen now? They're going to flow from negative to positive. Because there's a connection here, they're going to flow here like that, electrons. And as that is happening, there's a current. Okay, as that is happening, there will be a current. Copper will also release electrons as well, but it's not going to release as quickly as magnesium. So the one that is more reactive is the one that's going to release fast and quicker, and the electrons are going to flow from it to the other side because it's the first one to release. And that is basically what the current is. So what's going to happen now? The electrons that have been released, all right? If copper, we're going to have copper metal, but also copper ions as well, because even copper is releasing. So what's going to happen now? This copper that had lost electrons is going to gain back electrons, okay, to become copper atom. That's it. That's what's going to be happening now. So it's as if this copper is going to get thicker and thicker, or there'll be some deposits there because the copper ions are becoming copper. There, you see this? This magnesium is going to dissolve. It's as if it's going to dissolve because the magnesium is becoming ion. It was a metal, but now it's becoming ion. Now it's as if it's dissolving. So that's the idea. Now, if the difference in reactivity between these metals is very high, the potential difference generated will also be high as well. For example, if I use magnesium and silver instead of using iron and tin, the potential difference will be quite a lot. If I use the same metal, both sides, because the reactivity is the same, the potential difference will be 0. Okay? And at the same time, if I switch the magnesium and copper, the potential difference here will change sign. So if, say, for example, it was minus 4V, it will now become 4V. So if you switch these metals, then the thing will just switch because the direction of the flow electrons is changing as well. So this is just it. All right. So let's repeat now. So this copper ion is going to gain electrons, and when something gains electrons, we say it's being reduced, isn't it? So this copper ion plus becomes 0. So that means it's being reduced. The magnesium is going to be oxidized. Why? Because this magnesium is going to be releasing electrons the more. Are you getting that? So we have magnesium, all right? And this magnesium is going to release electrons, 2 electrons, to become magnesium plus. Do you see that? So you have magnesium atom, which is 0, neutral, and it's going to become magnesium 2 plus 2. That means it's being oxidized. It's losing electron, it's being oxidized. Okay? So I think that is just what this one is. Now, the voltage will drop over time because the chemical reactions, the products are going to run out. The reactants are going to run out. So when something is reacting, when the reactants run out, then the whole thing will just stop. Okay? So I want you to mark, that is question A, if you want to mark. Okay? And then I'm going to show you part B. Now I'm going to show part A. So part B is there. So this is it. So make sure that you can write all this in exam. Okay, so I hope you're happy with that. And part C, no, there's no part C. Now, question 9, we're going to go over production of ammonia. And then question 10, there'll be some other calculations. What I want to do at this point in time, I would like to I'm going to pause the video just for a minute. And then we will carry on shortly. We'll carry on shortly. So I'm just going to pause the video for a minute. Okay. All right, so we're going to carry on now. We're going to carry on now with question 9. I already show you the answers for question 8. Now you're going to move to question 9. Question 9 is going to be on, we call it Haber process. The process of manufacturing ammonia. The process of manufacturing ammonia. All right, suppose we didn't try this. This is just for triple. Hopefully you've done this topic before. If you haven't done it, you can leave it for now for your mocks, but for your final GCSE, you should be able to describe it. Suppose we didn't try this. Okay, now, before I go over it, the first thing we need to know, there's something special about ammonia, because ammonia is a gas. Ammonia is always a gas, NH3. That's what ammonia is, NH3, that's ammonia. But then you can then end up with ammonium, okay? This is a very important constituents of fertilizers that they use in growing crops, vegetables, and stuff like that. So ammonia is very, very important. And you can see that this ammonia has got nitrogen. Nitrogen is a very, very important nutrient in plants. Very, very important nutrients in plants. That's it. So that's what we have. So how do you do this one? Number 1, we need nitrogen gas. Number 2, we need hydrogen gas. Number 3, we need to react them together. To do this, we need temperature, high temperature, usually 450 degrees centigrade, and we do it at high temperature, 200 atmospheres, high pressure. And that's going to give us ammonia gas, NH3. This is a gas, and this is a gas, and this is a gas. All right, so this is the HAPA process. We are producing ammonia gas, and that ammonia is going to be reacted with other compounds to produce ammonium-based fertilizers that contain nitrogen that crops can grow. So that's the first thing we need to understand. The other thing we need to understand is that this reaction is reversible. As you can see, the arrows I've used. Nitrogen gas and hydrogen gas can react together to produce ammonia, but that ammonia can break up again to give you back this. So it's a reversible reaction, and you need an equilibrium. Now, one thing I want to say is that the forward reaction going this way is exothermic. Exothermic. Which means that when nitrogen and hydrogen react together, they release more energy than they gain. So increasing the temperature is a bad idea. It's a bad idea. Because if it's releasing energy and you're adding more energy, heat energy, then you are reversing the reaction. The forward reaction is exothermic, releasing energy, but you're also using high temperature 450. That is not good. But there's a reason for this. There's a reason for this one. If the temperature is lower than 450, which would have been better, let's say, for example, 300 degrees centigrade, the problem with that is that the rate of reaction is going to be so slow. More of ammonia will be released. The yield of ammonia is going to be a lot if the temperature is lower because it's exothermic reaction. However, if the temperature is low, the rate is going to be too slow. You're not going to get ammonia quickly enough. Yes, you're going to end up with a lot at the end of the day, but you're not going to get enough quickly enough. So the temperature needs to be a bit higher, 450. Anything higher than 450, like say, for example, 600 degrees, that will make the reaction go even faster, but that will be expensive because using energy, using heat, your electricity bill is going to go up. So 450 is a good compromise. You see this? Now, another thing also, in this case, the number of molecules of nitrogen, this side is 1. Actually, we should balance this equation first. So there are 2 nitrogen here, we need 2 here. Okay. And this side just there are 2. This side I've got 6. So I'll need to put 3 here. Okay. All right. So the number of molecules, there's 1 here and there's 3. I've got 4 molecules, if you can think of it, of 4 moles. 4 moles, and they have got only 2 moles. So basically, if the pressure is high, that's going to favor the forward reaction. It's as if when it tries to squash the 4 will become 2, like it becomes a smaller number. Think of it like that. So increasing the pressure is going to favor the forward reaction, that one. If you decrease the pressure, it's going to favor the reverse direction. You see this? So the pressure needs to be high. But can we make it even higher? Yes, we can make it higher. But the problem with that's going to be dangerous. When the pressure is so high like that, accidents can easily occur, explosions. And also, it's going to be really expensive because you need energy to maintain that pressure. So it's going to be very expensive and it's going to be really, really risky to do that. So 200 is a compromise. Anything lower than 200, the problem is that the reverse direction, the ammonia you're producing is just going to be breaking back up again. If the pressure is small, is lower than 200, it's going to be the reverse direction will be favored. Do you see this? So this is it. Now, how do you collect this ammonia? The ammonia is liquefied and is collected as a liquid. But the amount of nitrogen and the amount of hydrogen that has not reacted yet, because the reverse direction sometimes is very stubborn. Nitrogen and hydrogen, some of it are not going to react, or some of the ammonia will break to release nitrogen and hydrogen. So you need to pump this one back again to the system to react. So it's like a circular process. Okay, so this is the Haber process. Okay, now you can look at the explanations. That's 9. Now we're going to go to question 10, which is the last question. Okay, right, so now we're going to go to question 10. Question 10 is grade 9. I would like you to pause the video and try question 10. Pause the video and try question 10. This is for triple. Okay, right, so I hope that you tried question 10. The first thing they're asking us to work out the energy. Now, the energy released in a reaction is always equal to the mass times the space capacity times by the change in temperature. Remember space capacity, okay? Now, the mass of the solution is what we're talking about here because it's the temperature of the solution that has gone up. Okay? That's the first thing that we need to work out. Now, but the spare capacity they're using here is 4.18 joules. I would have said for solution, but they've said for water. Quite misleading, but it's all right because HCl typically is dissolved in water. So let's just use 4.18 as what they've given us, right? Now the change in temperature is 8.5 degrees, and the mass we're going to be using. Now, how do you work out the mass? Mass is density times volume, isn't it? Of the solution, not of magnesium, because the solution is made of so many things: magnesium, HCl, water, blah blah. So we're going to need to do the density, which is 1 times by the volume, which is 50, and the mass is going to be 50 grams. This is in grams. Now, I should have changed the mass into kilogram, but I'm going to keep it into grams because the spare capacity in terms of grams. So it's okay if the mass is in grams as well. If this was in kilograms, I would have changed this to kilogram. So the energy is going to be 50 times 5.1, 4.18 times by 8.5, and that should give us 1776.5. So that will give us 1776.5. So 1776.5 joules of energy. That's it. All right. Now, work out the moles of magnesium that reacted. Work out the moles of magnesium that reacted. Now, the equation has been balanced, isn't it? The equation has been balanced. So the 0.5 grams of magnesium is what they used. Let's assume that all of that reacted. Now the number of moles is always given by the mass divided by the MR or AR. The mass used is 0.5, but the AR, the atomic mass of magnesium, is always 24. So if you divide that, that will give you the moles that reacted. Right? That will give you the moles that reacted. And I think that's going to be around 2. Okay, around 2 point something. They've used 24.3, which is more exact, but it's okay if you just use 24 for Gcse. So this is the number of moles that reacted, 0.02 something. You see this? Now, if 0.02 moles reacted on magnesium, then 0.02, then HCl would be double because it's 2 here. That would be 0.04 and so on. Now, determine the enthalpy change in kilojoules per mole. Listen, 1776.5 joules is what has been released, what has changed. But that is for how many moles of magnesium? 0.02 moles of magnesium. So just focus on the magnesium. But they are talking about kilojoules per mole. You can change this to kilojoules by dividing by 1,000, and that will be 1.7765 kilojoules. But this is for 0.02 moles. We want for 1 mole. So we need to divide that by 0.002. That's what we need to do. Now, but let's see what they've just done. Let me just look at what they've done here. For part, where's that part? This is part B. We done part B, and then we're going to be looking at part C. All right, so part C, we have the energy that was released was this. It's negative because it was released. All right, but that was released by 0.02 of magnesium, focusing on the magnesium. But we want it per mole. So what do? We divide this one by the number of moles, and that will give us this. So that's a change in enthalpy. Are you getting that? Okay. All right, so that's it. So that's going to be that. We will leave it like that. All right, so now what I'm going to say is that if you're looking for videos, more videos like this, we've done question 1 to 10. That is AQA, paper 1, chemistry. You can also look, find physics and biology and maths in Mr. Owino YouTube, which is basically this. All right, teacher Mr. Owino. All right, others, thank you so much for today. That's going to be the end of this. Thank you.